Hi everyone, this is Shruti Gowda and I'm going to be presenting our paper Conserve, Update, Revise to Cure Generalization and Robustness Trade-Off in Adversarial Training. This is a joint work with Bahram Zunus and Elaha Arani, and this work has been accepted in ICLR 2024. Deep neural networks are pervasive in our modern world, serving as the backbone of various applications. Despite their widespread usage, deep neural networks are not impervious to challenges and limitations. They're susceptible to adversarial attacks, which are carefully crafted inputs that can lead to misclassifications. Adversarial training emerges as a promising strategy to bolster the neural network's robustness against adversarial attacks. However, there are still challenges. Firstly, the generalization and robustness trade-off. While adversarial training improves robustness, it often comes at the cost of performance on the natural or clean images. Secondly, robust overfitting. In standard training, that is on natural or clean images, as we train longer, the error decreases and the test accuracy increases. However, this is not the case in adversarial training. Prolonged adversarial training can lead to robust overfitting, which is a phenomenon where the model's performance and test data deteriorates. Adversarial images are subtly altered inputs that cause misclassifications in neural networks. For example, adding imperceptible noise to an image of a panda can deceive the classifying network into predicting it as a gibbon. Despite minimal visual change, the network's prediction drastically shifts, highlighting the potency of adversarial images. Thus, adversarial attacks can pose significant threats to AI system reliability and robustness. Standard training is the training on natural or clean images. It minimizes the objective function with respect to the model parameter using a natural dataset D, aiming for high generalization. However, it fails when inputs are imperceptibly modified. Adversarial training addresses this by generating adversarial samples during training, thus enhancing the network's robustness. Adversarial training involves a min-max optimization, where the inner maximization crafts strong adversarial examples and the outer minimization trains the model on these examples to improve the robustness. Despite significant research in adversarial training, a persistent knowledge gap exists in understanding the network's learning behavior when it shifts from standard to adversarial setting. Limited comprehension of this transition hampers the efficacy of proposed solutions, often overlooking the unique learning capacities of the layers of the network. Hence, we conduct an empirical study to investigate the behavior when transitioning from standard to adversarial training. We investigate the layer-wise weight initialization because the weight initialization and updates in navigating the two diverse data distributions is very significant. We also explore the similarity between features during both the phases of training. Further, an essential aspect of our analysis is the investigation of the overfitting phenomenon during the transition to adversarial training. For our empirical analysis, we employ a ResNet 18 architecture comprising of the 4 blocks and an additional linear classification layer. We adopt a systematic approach by reinitializing different layers of the network while keeping the remainder fixed. We create 12 different combinations. For instance, for example, in the figure shows U23, which means blocks 1 and 4 are frozen while block 2 and 3 are updated. The natural and adversarial accuracy of multiple models on CIFAR-10 dataset is shown in the figure. ST and SAT in the graph represent the accuracy of standard training and adversarial training respectively. As shown, focusing adversarial training solely on early network layers leads to reduced performance on both the data distributions. And updating specific layers, particularly later ones, mitigates accuracy decline. because they leverage the fixed representations in earlier layers for enhanced learning capacity. These findings suggest that training the entire network without selectively updating the parameters may not be the most optimal for adversarial training. Visualizing the features learned on natural and adversarial data and examining the differences helps to understand the representation alignment. For this, we employ this metric centered kernel alignment or CKA. In standard training, there's a noticeable dissimilarity in representations, highlighting the inherent difficulty for naturally trained models to excel on adversarial data. Conversely, adversarial training yields similar early layer representations but diverges in the final layer due to design perturbations that alter the decision boundaries. In experiments and on the other updated models, models selectively updating final layers exhibit greater similarity and lesser block structures in the representations. Thus, optimizing parameters to promote alignment between these features, which are robust and non-robust, and learning a generic representation between the distributions holds promise for achieving a better balance. We also explore robust overfitting phenomenon. The figure uh, here represents the test accuracy curves for all the models, and we can consistently see the trend of declining accuracy beyond a certain threshold. The base or the adversarial training model prominently exhibits overfitting. When we selectively update early layers, we observe a reduction in overfitting tendencies, albeit at the cost of lower overall accuracy. For example, U1, U2, and U12. The middle layers play an important role in balancing between reducing overfitting and also having higher test performance. And in the graphs, U23 model stands out with relatively stable test accuracy. Thus, it suggests that selectively updating the layers plays a role in mitigating robust overfitting while maintaining competitive performance levels. We find many interesting findings from our detailed empirical study. Firstly, uniformly training the network and updating all the weights might not be optimal for learning the two different data distributions. Selectively updating certain weights while conserving others can effectively leverage the network's learning capabilities. Thus, by considering the retention and learning capabilities of the network, a better balance between natural and adversarial robustness can be achieved. Based on these insights, we propose a new adversarial training framework that incorporates selective weight updating for enhanced performance. Our method is based on three key components: conservation of knowledge from natural data, updation of knowledge from adversarial data, and revision of consolidated knowledge. Thus, CURE. Instead of manually fixing and updating the layers as in our initial empirical analysis, we devise a technique to dynamically update the weights of the networks in each layer based on an importance criterion. Consider a deep neural network and classify or parameterized by theta. X natural and Y represents the natural images and labels. The network is trained on natural images using the standard training schema. And we use this pre-trained network and move to the adversarial training setting. Adversarial samples X adversarial ADV are generated during training for each clean sample by adding a perturbation delta. And we introduce a novel, robust gradient prominence criteria whose objective is to facilitate the selection process by identifying weights with the greatest influence on model predictions through the gradient scores. By dynamically determining which weights to update based on the importance of both natural and adversarial samples, RGP aims to optimize the performance on both distributions while avoiding skewed results. Based on this RGP score, a gradient mask is created by removing a fraction of weights with low prominence score. The gradient mask is applied to update only the most important weights. RGP ensures that firstly, we conserve past knowledge by preventing a fraction of weights from updating. Secondly, learn new knowledge by updating weights that have the capacity to learn without overwriting. And thirdly, utilize the network's capacity efficiently to achieve balanced performance. Another stage is we introduce a revision stage to consolidate knowledge across all the patterns and obtain a more balanced performance. Stochastic updates to the revision help accumulate knowledge throughout the training. And this consolidated information is shared with the training model through a consistency regularization objective. This regularizes the knowledge flow from the revision model to the training model. Coming to the results section. We benchmark our methods on various architectures, datasets, and attacks, namely PGD, CW, and auto attack. We also introduce natural to robustness ratio or NRR to get a more balanced metric between standard generalization and adversarial robustness. In the table, NAT denotes accuracy on the clean test set, and evaluations include PGD20, CNW, and auto attack. The table also features methods that incorporate more than one model in the training, which is categorized by a line in the second part. Notably, CURE achieves the highest NRR among all the methods, showcasing superior performance in balancing both robustness and natural accuracy. For instance, when considering wide ResNet 34 model, CURE outperforms traits by 2.5% on PGD, FAT by 10% on auto attack, and multiple teacher-based technique IAD by 2.3% on CW attacks, all while maintaining the highest natural accuracy. We also report visualization of different analyses. Firstly, generalization versus robustness trade-off. As shown in the figure, CURE strikes a balance by selectively conserving weights, ensuring robustness without a significant decline in the natural accuracy. Secondly, we show the performance under varying levels of attack strength perturbations. CURE consistently outperforms other methods like AT, traits, and MART. Thirdly, robust overfitting. While traditional methods experience declining test accuracy for adversarial data due to overfitting, CURE effectively mitigates this issue. Observations about robust overfitting are further supported by the results presented in this table. CURE achieves the highest test accuracy at the end of training, indicating a delta value of 0, which signifies no decline in the performance. As shown in the table, it outperforms all the other state-of-the-art methods. Thus, the inference is that the sparse update technique used in CURE not only achieves an improved trade-off, but also offers the remarkable outcome of reducing robust overfitting. Additional results on datasets such as CIFAR 100 and SVHN are shown in the table. CURE outperforms all other methods even in the face of challenging attacks like PGD with higher steps, example PGD 100 and CNW. Deep neural networks are also prone to natural corruptions, leading to inconsistent predictions, especially in safety critical applications. To assess model robustness, we introduce various corruptions and evaluate performances on 15 different types of corruptions. These 15 types are grouped into 4 categories, namely blur, digital, noise, and weather corruptions. CURE focuses on balancing knowledge retention and learning from different distributions, thus enhancing model stability and overall robustness against diverse corruptions. Further, we also visualize adversarial perturbations that showcase the minimum perturbations needed to deceive each robust model. For example, in the figure, we see that CURE requires a larger perturbation. These values are displayed below each image. So CURE requires a larger perturbation to make an incorrect prediction compared to other methods. This means that it is more difficult to deceive models trained with the CURE framework. Further, CURE also preserves semantic features better compared to other methods, necessitating modifications to semantically meaningful pixels for deception. Thus, overall, models trained with CURE exhibit heightened sensitivity to perturbations, requiring alterations to important object features for successful deception. This highlights the cue's effectiveness in preserving the integrity and robustness against adversarial attacks. Thank you very much. And here is my details in case you have any further questions or comments. Thank you.